sklearnsvmNuSVC. Description: NuSVC is a support vector classification SVC model that uses a parameter nu to control the number of support vectors and the upper bound on the fraction of training errors. It is similar to SVC, but it provides more control over the number of support vectors and the trade-off between model complexity and training error. Inputs: X training data, represented as a 2D array of shape n samples. N features, where n samples is the number of samples and n features is the number of features. Y target values, represented as a 1D array of shape n samples, where each element corresponds to the class label for the corresponding sample in X. Outputs: Self: the trained NuSVC model. Decision function X returns the decision function values for the given data X. Predict X returns the predicted class labels for the given data X. Steps: The NuSVC model constructs a hyperplane that separates the data points into different classes. The new parameter controls the number of support vectors and the upper bound on the fraction of training errors. The model finds the optimal hyperplane by maximizing the margin between the classes while minimizing the number of support vectors. Metrics: Accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly classified positive samples among all predicted positive samples. Recall: the proportion of correctly classified positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Visualization plots. Decision boundary plot visualizes the decision boundary of the trained NuSVC model, showing the separation between different classes. Scatter plot with support vectors visualizes the data points and highlights the support vectors used by the model. Fine-tune parameters. Nu: the parameter that controls the number of support vectors and the upper bound on the fraction of training errors. A lower value of nu will result in fewer support vectors and a tighter decision boundary, while a higher value will result in more support vectors and a looser decision boundary. Kernel: the type of kernel function used to map the data into a higher dimensional space. Common kernel types include linear, poly, RBF, and sigmoid. The choice of kernel depends on the characteristics of the data and the desired model complexity. Degree: the degree of the polynomial kernel function. Gamma: the kernel coefficient for RBF, poly, and sigmoid kernels. Coa 0: the independent term in the kernel function. Uncertainty methods. Confidence scores: the decision function values can be used to estimate the confidence of A. Predictions. Higher absolute values of the decision function indicate higher confidence in the prediction. Out-of-bag error for models trained with bootstrap aggregating bagging. The out-of-bag error can be used to estimate the uncertainty of the predictions. Challenges and fixes. Challenge 1: overfitting. If the model is too complex, it may overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in Challenge 1: a NuSVC model with a high degree polynomial kernel and a low nu value may overfit the training data. Fixes to Challenge 1: reduce the complexity of the model by using a simpler kernel function or a higher value of nu. Use regularization techniques, such as L1 or L2 regularization, to prevent overfitting. Challenge 2: high dimensionality. If the data has a high number of features, it may be difficult to find a suitable separating hyperplane. Sample use case that resulted in Challenge 2: a NuSVC model trained on a dataset with thousands of features may struggle to find a good decision boundary. Fixes to Challenge 2: use feature selection or dimensionality reduction techniques to reduce the number of features. Consider using a different type of classifier that is better suited for high-dimensional data, such as a random forest or a gradient boosting machine.